And I have the pleasure tonight of introducing our guest speaker, Rob Butler. And this is not the first time that Rob has given a talk for the Northwest Highlands Geopark. We're super grateful to welcome him virtually into the Northwest Highlands tonight. If ever you want any questions answered on how mountains are made, Rob is your man. And tonight he's going to tell us all about discovering the Moine Thrust. So I'm super excited, and you're already sharing your screen, Rob, so why don't you dive right in?
Thank you very much. I hope you can hear me. You can just confirm that my sound is getting through.
That sounds good to me.
Brilliant. Good. Well, thank you everybody for joining us this evening. I thought it might be nice to talk a little bit about the Moine Thrust and its discovery. If I just click on, hello, can I get my slides to advance? That's interesting. Let's try that. Good. So this outcrop, which is in the Northwest Highlands, a place called Knocken Crag, I'm sure many people on the call tonight will have been there, perhaps not with the blue sky. And these outcrops are some of the most famous in world geology, certainly in world tectonics. And to put that in perspective, next month, the IUGS, which is the International Union of Geological Sciences, essentially a sub-body of UNESCO, will announce its 100 top global geosites. There are two in Scotland. One is Siccar Point, of course. The other is the Moine Thrust Belt. So it's world importance. And I thought it might be quite fun to review why it's important. And it's much more to do with the history of geology and how it came to be discovered and the knowledge developed subsequently. It remains a really important place for field training. As you can see in the photograph, the herds of Aberdeen students, when we used to have herds of students walking across to get a closer look. So what they're going to have a look at when they get across the bog is at the end of that arrow there. This is a cross section we'll revisit at various occasions through the next hour or so, and we'll talk a bit more about it as we go. But what the really critical point about this image is that there's a major contact through there that I've just animated up in red, which is a thrust. The arrows tell you it's a low angle fault that's carried those yellow rocks that form the Cromot Hills over the other rocks underneath. It's a thrust fault. The Moine Thrust and its equivalent structures in the Northwest Highlands are amongst the first structures like this that were ever described on the planet. And you might think, fine, okay, nice structure. But actually thrust faults are probably the most important, some of the most important tectonic structures there are. And to emphasize that, let's take a deviation away from here and look at some examples of thrust faults. So here's an example from the other side of the world, about as far from the Moine Thrust as you can get in a hillside above Auckland in New Zealand. And just to explain what a thrust fault is, it runs through there. It's a fault that has offset those black markers and the other markers in there, something like this. So thrust faults are responsible for accommodating the lateral squeezing of rocks together. And one way they might do that is to fold, but when they fault, the faults they make are thrust faults. So they're really important structures, but they're more important than even this rather cute one in New Zealand. Here's the thrust fault. You might know that better as a subduction zone, but a subduction zone is an example of a major thrust fault. It's as big as they get. And in this particular case, which the block diagram that I've lifted from the USGS shows a cross-section or block diagram through Honshu, Japan, and it shows the floor of the Pacific Ocean being taken down beneath the island of Honshu in a subduction zone. And the reason that, of course, that this is important, not only is this important for general tectonics, it was also kind of important for the occupants on the eastern coast of Honshu, because in 2011, bang, there was the Tohoku earthquake, which is arguably the largest earthquake ever recorded, that went pop there. Just to explain how that works, I've drawn a little cross section at the top in a really Mickey Mouse fashion, which shows the floor of the Pacific Ocean in that sort of tan color going beneath Japan in the green bit in there. And the way the earthquake builds up is that essentially the fault, which is the black bit, sticks a little bit, so that as the downgoing plate continues to go down, it drags the overriding plate with it like this, but it can't maintain that for long. Essentially, that stickiness eventually fails, and bang, you get the earthquake. And the reason, of course, that this was such a big deal was that earthquake and the fault was submarine, and the effect of that was to generate the tsunami that caused such devastation along that part of the coastline. So thrust faults are kind of important. They are responsible in this setting for the largest earthquakes that are experienced. And of course, they're also responsible for stacking up the crust. This is the historical diagram from the Swiss geologist Emil Argon, but it's not through Switzerland, it's through the Himalayas in Tibet. And it shows his idea of India, which is the bit on the right-hand side where it says Fig 13, diving underneath Tibet, thickening the crust up. The faults that are doing that, those tectonic processes, are thrust faults. Moving downscale a bit, just to emphasize the importance, this top cross section is a colored up version of a very famous cross section for those of us in the business, drawn by Bert Bally and others in 1966, or published then, which is through the foothills of the Canadian Cordillera in Alberta. And those vertical black stripes are oil and gas wells, which were producing and indeed continue to produce hydrocarbons from the foothills area. So thrust faults have been really important for economic resources. Worth pointing out while I'm talking that thrust systems in front of the Alps now are in Switzerland are the active places where the Swiss nuclear regulator will have to store nuclear waste. So thrust faults and understanding them are important for the societal challenges of dealing with industrial waste, not just producing the carbon dioxide. So these ideas of thrust systems have their roots in Northwest Scotland. And so what I'd like to do is, having established why thrust systems are important, is explore how this knowledge was won. So here we have a bunch of students discovering the Moine Thrust belt and its associated structures. In fact, they're riding the wave of the Moine Thrust sitting above the crag at Knocken, which was the view we were looking at the start of the show. So what I'd like to do is to explain how the knowledge was created that we've been able to share with generations of students since, and many others, of course. So where are we? So here's a summary geological map of northern Scotland. The Moine Thrust is this tectonic feature that runs down from the north coast down towards, and indeed onto, the Isle of Skye down there. And on the right-hand side, which is above the fault, are the yellow rocks, an area generally referred to as the Moine. And this is the interior of an old mountain belt, and it's been carried out across rocks on the left-hand side, which are generally referred to as the foreland. They've been carried in the direction of the arrow. So there's a major structure there that's the Moine Thrust and its associated structures that are responsible for carrying the Moine, the old basement rocks, the old interior of the mountain belt across apparently less deformed areas in exactly the same way as if you like, that Tibet has been carried across the Indian subcontinent on that diagram that we looked at a few slides back. That's fine, but why is it so useful as a training place? Well, the really key part about it is that the rocks are relatively easy to identify. This vertical section here shows essentially the stratigraphy, the rocks that lie beneath the Moine Thrust that have been buried and caught up by it. And they're almost easier to distinguish in the field than the colors are on my diagram. which makes it really great. One of the real challenges in taking students into the field is them getting hung up about what rock unit they're in. And so they spend a lot of time worrying about what the rocks are, rather than, in this particular case, worrying about the structures. And the real advantage in the Northwest Highlands, in this particular ground, is the rocks are relatively easy to distinguish. Therefore, we can quickly get into the tectonic complexities and really scramble their brains with those. So it's a good place to play. So let's just look at the Moine Thrust in a rather remote place on Craig and Milhorn, which is just behind the mountain massif of Foinaven. And you can see the contact there, carrying those dark rocks, the Moine, over a little slice of limestone, which is the beige stuff poking out of the grass. So that's the Moine Thrust away from the popular areas. Now, as you go south in the Moine Thrust belt, particularly south away from the area that I've got in the photograph, the stratigraphy involves even a patch of older rocks, which are informally known as the Torridonian sandstone. And those add an extra part to our stratigraphic template that gets caught up by the thrusting process. Now, the real neat thing about the Moine Thrust is that it's not alone. It's come with a whole bunch of other structures, and it's these that are really the really wonderful things to start playing with. And just to emphasize this, I'll take us down to a southern part of the Moine Thrust belt and have a look at the landscape. So what this landscape shows in the Achnacheilloch forest, which is sort of near between Strathcarron and Torridon, is a landscape that is made geologically by stacked up Torridon group rocks, the brown bits in our column, and the lower part, well, actually indeed most of the Erebor sandstone formation. And the colors stand out in the ground, but I'll just add the graffiti. Tor for Torridon group, ESS is Erebor sandstone. And you can see in this landscape that these units appear several times, and they're stacked up by thrust repetitions. It's some of the most dramatic and clearest thrust stacking I've seen anywhere on the planet. It's fantastic. It's a shame, but in some ways good, that it's a bit of a walk to get to, but they're dramatic and it's worth the walk. So let's move on. So here's a cross section that was put together and was published in 1923 in a very famous map. Again, I'm sure many of you have seen it, and we'll look at it as later on in this talk. That cross section from 1923 and ones like it have been rebuilt and reinterpreted subsequently. So the work that we will look at this evening about how these structures were found formed the basis of more research in the later part of the 20th century. And the diagram below there by Dave Elliott and Mike Johnson reinterprets part of a cross section that was drawn actually in the 1880s. It heralded the start of a renaissance in understanding thrust systems, in part taking the ideas from the Canadian Rockies, the Bally et al. Section. And it's been taken forward to really establish the ways in which these systems work in a way that makes structural geology very predictable when it comes to interpret the subsurface. And those ideas have been taken forward subsequently. So here's a cross section that was drawn by Hannah Watkins, who did her PhD in Aberdeen with us quite a long time ago now, it seems, by looking at that date. And this cross section was through those areas in Achnacheilloch, showing the brown Torridon group rocks stacked up on the blue and other units, which are the younger Cambrian strata. So the work has progressed. It's providing more precision and better understanding of how these thrust systems work. But I've sort of jumped ahead a bit. I want to go back in time. So how did we get to that level of knowledge that we have today? So let's go back to Nocken, and we can start the debate back here, not in the 1960s, but in the 1860s. And let's just look at what the rocks are up here. So you go through some really distinct rocks. You can even recognize them from several hundred meters away on the other side of the valley, where you've got the rock units as I've labeled there. And as we're looking at the cliff, the rock layering is running almost horizontally, apparently horizontally. Now, this cliff section, one of the first visitors there was a guy called Archibald Geekie. And this is a photograph of his field notebook that's kept in the Hazelmere Museum in Surrey, which Geekie essentially more or less established, and has his archive in. So this is his field notebook, and what it shows is quite a lot of detailed description of the rock sequence up through there, and it shows the idea that the rock layering is inclined into the hillside. So as we look at the photograph behind, it would be inclined, dipping rather gently back into the hill. So he took that understanding and developed a relationship between all the rock units. He wasn't working alone. He was also working with Roderick Murchison, who was essentially his boss. Murchison was the Director General of the Geological Survey, and Geekie was a new hire who was essentially the guy who ran around looking at the rocks, while Murchison basically told him where to go. So this is a diagram that now lies behind it there in black and white, which is from their 1861 paper that reports the fieldwork recorded in Geekie's notebook. And the really critical thing on here is that contact in black. It's the feature that we now call the Moine Thrust. But back then, back in the 1860s, such ideas were not even in their dreams. So what we have is a rock sequence with a black line there, which records the abrupt transition up into the rocks on top, which they called gneiss schist. And the photograph on the left is what it looks like. It's a very platy, flaggy looking rock, but it's nevertheless metamorphic. Indeed, Murchison Geekie spoke about its character and that fine layering as if it was a flagstone, like you see in cinches like Yorkshire flagstones or Caithness flagstones. So imagining that's sedimentary stratification. The key point is that they noticed that everything was parallel and gently inclined into the hillside. They therefore assumed that the rock sequence was conformable. It was a simple stratigraphic package, and the youngest rocks in this succession were the ones that are on top, which are the gneiss schists. Metamorphic on top. Now, they were concerned about that, but not so concerned that they wanted to disregard the idea that this was a conformal contact. Indeed, in the same field excursion, they then shot off into the middle of these units into the ground to the east of Ullapool, looking for a reason for the metamorphism. More of that in a minute. So here are these guys. So I thought I'd show them pictures. There's Roderick Impey Murchison holding an ammonite in rather grand surroundings on the left, and Archibald Geekie in similar grand surroundings with an umbrella, because he's just off in the field. And there's a diagram at the top which they use to explain how the rock sequence works across northern Scotland, where you go from various rock units, but they basically get younger from left to right in a simple stratigraphic succession. Yes, there could be some folds, but they don't really do very much except take all the rock units and fold them all together. Right. Next player on the scene is my academic ancestor, a professor. He's the first professor of natural history in the Unified University of Aberdeen, which was unified in the mid I should know this. I'll get banged back for this in the middle part, at least, of the 19th century, and he was working in the area at the same time as Murchison and Geekie, and this is his cross section through the Knocken area. I'll just zoom in on the right-hand side, which is the critical ground there. So he has his unit A on the right there with the sort of squiggly bits would be the gneiss schist of Murchison and Geekie. For nickel, he's just called this gneiss. The other rock sequences, which were sedimentary, which form the lower part of Knocken Cliff, are shown on the left-hand side of that diagram, capped by unit D, which is limestone. And for nickel, the contact between the two is marked by that strange squiggly stuff with the X. And he argued that the metamorphic rocks, unit A, had to be faulted in. They're metamorphic, they can't pass up from the sedimentary rocks underneath. And he said, therefore, this contact was a fault. Now, here we have the first really important deviation between nickel and Murchison. It's not to do with the cross section, but more the ways in which they develop geological knowledge. Murchison and Geekie used and faithfully record, as we'll see in a second, the field relationships. Nickel approached it theoretically. He said the metamorphic rocks had to be faulted in because you can't conceive, or it's incompatible with a theory that says they could lie simply on top of a normal stratigraphic package. So they must be faulted in by theory. Next part of that theory is, well, in the middle part of the 19th century, people's understandings of faults were they had to be steep and essentially subvertical. Therefore, if the contact between metamorphic rocks and sedimentary was a fault, that fault had to be steep. And there was an even bigger additional component to this idea, which is that faults are at the time were seen, as indeed they are, the consequence of an unstable Earth's interior, and therefore, in a 19th century, early 19th century world, an unstable Earth interior was a volcanic Earth interior, and that faults must therefore be associated with igneous rocks. So on Nickel's diagram, his X unit is igneous rocks intruded along the contact. So that cross section is largely based on a theoretical understanding of how the Earth should behave from the standpoint of the middle part of the 19th century. So we have a dispute. So let's look at the contact. This is obviously not a photograph from the middle part of the 19th century. It's one from 2 weeks ago. And it shows the contact. Well, let's zoom in. There it is. You've got limestone, and on top there, the gneiss schist in Murchison and Geekie's language. And there's the contact. You can see why they think it's conformable, because clearly in the field, it's a low angle contact that is more or less parallel, not only to the layering in the overlying gneiss schist, but also to the geological boundaries in the sedimentary strata underneath. So that's what it looks like in the field. It's not a vertical structure, and what's more, there are no igneous rocks along it. So we have competing interpretations. The top one, Murchison and Geekie, the bottom one, Nickel. The top one honors the structure. The relationships that we see in the field are faithfully reproduced in the cross section, but the metamorphism is ignored. In Nickel, the metamorphism is explained, but he doesn't honor, he's not faithful to the field relationships. So if a jury had gone to Knocken in 1861, when these diagrams were produced, they would have had to say that Nickel was wrong. In any event, everybody said Nickel was wrong anyway, because Murchison and Geekie were in the geological survey and part of the geological establishment, whereas Nickel, even though he was in an ancient university, he was not in the seat of power in Aberdeen. He was not in Edinburgh and London. So therefore, he was essentially shouted down. So in 1861, Murchison and Geekie win, and their ideas that there's a conformable sequence is played out. So they failed to discover the Moine Thrust. They said there's stratigraphic continuity. There are no significant faults in the section. So what we have here on the photograph on the left is the geological survey in 1868. Time's moved on a bit. Geekie, no longer a new hire to the geological survey, is actually the local director in the Edinburgh office of the geological survey. So essentially ran the geological survey of Scotland, and as a consequence, he was responsible for putting together the quote unquote definitive geological map for Scotland, a scene of which is on the right there, and it shows slightly later than this in the 1870s, it shows the idea of, well, no faults at all, and a very simple structure running across the highlands, where the rock units essentially continue as a conformal succession, getting progressively younger from west to east. Right. Well, all good as far as the survey is concerned. And the world is working nicely. It's a relatively simple piece of geology. Geeky essentially doesn't do much else for a bit. On this photograph are two other characters who are about to come to the fore, John Horn and Ben Peach, and we'll meet them again shortly. But first, we have to introduce two new characters, and our story's moved on to about 1880. These two characters here, they look like they're sort of extras for some Dumbledore Appreciation Society, but they're not in Hogwarts. They're in essentially two academic geologists who are about to enter the fray. And one of them is exceptionally well known to geology. He's the one on the right, Charles Lapworth, who did a whole bunch of exciting and really super important things. The other one is Charles Calloway, who to many people has been airbrushed out of the story, and as I've put in the caption here, is the unsung hero of Highland geology. So let's look at what they did. So Calloway worked in various places in about 1881 and 82. And in 1883, presented a paper to the Geological Society, which was the gathering point to share geological knowledge and understanding, and said this: of this view, which is Loch Glencool, by powerful lateral thrust from the east, the Caledonian, in other words, the Moine or the gneiss schist, was forced up beyond the fault so as to double back the ascent rocks, the Cambrian, and overlie them for some distance. In other words, he's talking about faulting, and he's talking about faults that don't move vertically, but move horizontally, in other words, laterally. Here's his cross section. As I said there, it was presented at the Geological Society in May 1883. Here is the contact he was first referring to. The shaded bit on the right is the gneiss schist, or the Moine rocks, carried by a structure there. I've added the arrow to show the direction he was talking about, but he was clearly talking about it moving to the left towards the west. And there's another structure, which is the one in the photograph here, a thing we now call the Glencool thrust, which carries the unornamented white part of this diagram, which are old basements. The Hebridean is what he called it. We now call it the Lewisian in general, over those layered rocks, which are the Cambrian. So he presented that in 1883. Well, okay, well, what was Geeky up to as this was going on? He wasn't actually in the audience. Oh, I forgot. This is my most. Here's a little bit of new insight that I've dug out. It's not new at all because it goes back to 1883. It wasn't just Calloway. At the same time as Calloway was producing that paper, in the field was a guy called John Blake, who was just being appointed as professor of natural science at what is now Nottingham University. And he had also a tour around the Highlands and came up with this section across Glencool. He has a thing called moving gneiss. In other words, it's a laterally moving or emplaced sheet of material on a sliding fault, something we would now call a thrust. Indeed, this is a pretty good representation of the Glencool thrust, looked at in the opposite sense to the one that Calloway did. He also was fully aware, if you read the text underneath, that there was going to be a big argument in geology, because he basically likens the change in ideas that are coming from his work and Calloway's to a rising tide that will wash the previous ideas of stratigraphic continuity from a rock by the sea, and it's about to get washed away by new knowledge, as indeed happened. Right, so let's go up to Erebor, because the other player, the player that everybody knows about who knows this story, is Charles Lapworth. And Lapworth was working up here in 1882 to 1884. In fact, John Blake visited him in the early part of 1883, so it's possible that indeed quite likely, that Blake was sort of trained into looking at rocks, quote unquote, the correct way by Lapworth showing him the ground at Erebor. And this is one of the famous structures at Erebor that Lapworth found. It's a structure we now call the Moine Thrust. It's one of the clearest examples you see anywhere, with the gneiss rocks on top, now a unit we now call the Lewisian, which is the sort of greenish, grayish material on top, and then the lighter color material underneath are Cambrian sandstones. So he recognized the idea that there are major faults that carry rocks in sideways. So what's going to happen next? Let's go back to Geeky's map from the 1870s. A few years later, Geeky, who is still in a position of drafting maps, will draft a map that looks like this from the 1890s, which shows much more detail and shows, although it's hard to pick out on this, a fault contact that runs the length of the map from the coast down to the bottom left-hand corner. So the question is, how do we get to that stage? What the story I've told you so far is of a survey that thinks there's stratigraphic continuity, and a bunch of people, many that they largely regard as renegades, who are saying that they're wrong and that they're low angle faults. Well, what's Geeky about to do? Well, in 1882, just as Callaway and Lapworth and Blake are about to present their work, Geeky becomes Director General of the Geological Survey. I've shown another one of Geeky's, or a similar version of Geeky's map, slightly different colouring scheme from the 1870s, which shows the level of geological knowledge for northern Scotland, which bluntly is pretty crude. In contrast, England and Wales by 1882 had pretty much had a complete coverage of 1-inch geological maps. The Highlands of Scotland didn't have any. So Geeky's main task when he took on the Director Generalship of the entire survey of the United Kingdom was to mobilize his forces with a view of creating the 1-inch map coverage for the Highlands of Scotland. So where was he going to do that? His mission, his view was, well, we need to start somewhere where it's simple and there are fossils that are described, and we can work from there and start building out. So the place he chose to do that was Durness. So what he did was he sent 2 of his best people up to the Durness area in 1883. I should say that's not a photograph from 1883. Those 2 guys were Ben Peach and John Horn. I thought rather than show the normal pictures of these guys, I thought I'd show some sketches by their colleague Henry Caddell, which sort of captures their characteristics rather more than the set piece photograph. So they went up there in 1883. What's quite interesting is the timing of that. They went up there in June. They went there more or less as Callaway in London was presenting his findings that said that there were major low angle faults. Indeed, Callaway also presented maps of the Durness area, which showed low angle faults in that area too. But Geeky didn't take Callaway seriously. He didn't think he was a proper scientist, it seems. And so he basically said, okay, Peach and Horn, go and start here, sort out the stratigraphy, get some mappable units and start mapping from there. This is their combined field slip. Most of this is the work of Ben Peach with extra comments from John Horn. And that map sheet is a remarkable piece of really detailed work. Lots and lots and lots of information. So they did a really good job at recording what they hoped would be a nice foundation stone from which they could work from. Indeed, this is what Geeky said in his annual report for that year, was the idea was that this area would serve as a baseline from which all our sections across the Highlands will run. So once you sort this out, you can then build out from that. There was an additional point, which is really quite remarkable. They mapped that field slip that I'm showing on the screen at the moment. You can't get the scale of it, but it was actually a map sheet of 6 inches to the mile, or 1 to 10,560. Super detailed. The idea was that having got this key area sorted out, the rest of the Highlands we mapped at the scale of 1 inch to the mile, 63,360. So hugely less detailed. That was Geeky's plan. And on the basis of that, he basically proposed that the Highlands would be mapped in 11 years with the existing staff of the Scottish office. Ambitious. Right, so this is the compilation of that mapping at a scale of 1 inch to the mile, published, as you'll see from the right-hand side, in 1892, so quite a long time afterwards, for reasons that hopefully will become clear shortly. And that's where they mapped. In the meantime, remember, this is 1883, they're working there. In the meantime, down here, in this corner, is where Lapworth is working in 1883 and telling Blake and one or two others about how the geology works. In 1884, Peach and Horn go over there. And indeed, the mapping you can see on here is not Lapworth's, it's Peach and Horn's mapping on the eastern or the southeastern side of Loch Erebor. So they come on the scene. They don't discover as original geology the idea of thrusting there. What they do is they repeat essentially the quote unquote experiment that Lapworth has performed and confirm his results. So at the end of the season in 1884, which was only about 6 or 7 weeks, Geeky went up there and was confronted with this. And rather famously, this is what he said. When a geologist finds nice overlying gently inclined sheets of fossiliferous quartzite shale and limestone, he may be excused if he begins to wonder whether he himself is not really standing on his head. So he goes on in this paper published in 1884 to coin the term thrust for these structures, claiming the insight to be his and his survey colleagues, airbrushing out not only Callaway, but Blake and Lapworth out of the story, which caused a massive ruckus, which is quite well documented. And I don't really want to go into the fallout of that now. We can in discussion if you fancy. So let's have a look at the mapping that Ben Peach and John Horn did. And this is the nature of the ground if you've not been up there, again on an unusually blue day. And here is largely Ben Peach's field stick for just adjacent to that area. And it shows lots and lots and lots of detail. And you'll notice that the sea is used to cartoon up really detailed sketches and little cross sections. Here is the same, a slightly larger map area that is in a compilation that was largely the responsibility of John Horn to compile up the results of different surveyors and to put essentially a definitive 1 to 10,000 map together, which they called a clean copy. Again, they transposed the detailed sketches rather more clearly into the sea, so you get an idea that little bits of cross section and detailed mapping. But you look at the detail on that, lots and lots and lots of little thrusts that create a sort of zebra map pattern of slices of different rock units stacked one on top of the other. It's really, really exceptional. Right, so 1884, Peach and Horn have basically got the tools now. They've been to the right ground, the ground that Lapworth worked on. It's super clear. There's no really doubting what the structure is. They've abandoned the idea that there's a conformal rock sequence, and they now tooled up to work through the area. And I get the full geological knowledge. They move, Geeky quite quickly abandons the idea that this could be carried out at a scale of 1 inch to the mile, and he retains the idea of mapping at 1 to 10,560. He also realizes that the rest of the Scottish office should get involved with this, not necessarily mapping the ground initially, but getting the understanding that comes from the rocks around Loch Erebor and in Northern Assynt. And so he basically encouraged his team to go up there. And they went up there in 1885 at the start of the field season. This is a team photograph, very famous one, where they stylized themselves as the bandits who are going to go and potter around. So our friends Peach and Horn are in here together with 2 other members of the Moine Thrust mapping team, as it would become, Hinksman and Gunn. There are others as well. It's thought that this photograph was taken by Henry Cadell, because he's not in the photograph, but he was part of the team. Right, so let's see how they did. So let's go and look at, I could show you dozens of examples of really fantastic mapping, but I'll just show you one, which comes from this area here at Loch Glencoe. And this area was mapped by Charles Clough. So here he is, Charles Clough, and this is one of his field maps. I deliberately picked one of the ones that isn't very complete so we can get an idea of how it was done. So I'll just zoom in to this area here. You can see the geology forming that sort of slug-like shape coming off the sea and running across the left-hand, halfway up the left-hand side of the map, which shows the precise way he's mapped out slices and slices. You can get the idea of these rocks being sliced up and stacked on top of each other there. And there's lots of annotation describing his observations in there as well. But the really remarkable thing about this, I think, is if you look, he's drawn the topographic contours on. This base map, it was state-of-the-art base map at the time in the middle part of the 1880s, but the Ordnance Survey here had only mapped the hydrological features, the streams, some major fence lines, and the shoreline. They didn't map the topography. That was down to the surveyors. So they dotted in, they had to map the topography as well as the geology as they were going along, which is, I think, quite remarkable. So that shows the map in a fairly incomplete fashion. I'll show you another one of his field slips, which is more complete. Indeed, it's completely complete. He hasn't coloured in the gneisses. They're basically white, apart from some of the various intrusions that are in it, which is that red stripiness. So that's his rather, you can see what the weather was like. It looks somewhat distressed, this field map. It's been, it's been sort of stuck together and it's sort of falling apart. So there's the field map, stacks of information. And what happens to that is that this map is then taken and it's used by subsequent people to add further information on. So it becomes quite difficult unless you can work out whose writing is who about how the observations relate to an individual geologist. But regardless of that, it's compiled largely by John Horne into this spectacular so-called clean copy map for the area, again at 1 to 10,560. And then that in turn is used to create the published map. And this is the published 1892 Loch Inver sheet. And the red box there is the little bit we've been looking at. So the published version is a simplification of the super detailed mapping that was done. Incidentally, this map, and we'll see it shortly, this map was printed in black and white, and then it was painted before its sale in superfine watercolor. So you bought from your map outlet, presumably directly from the survey or Her Majesty's Stationery Office, it was Her Majesty's Stationery Office at the time, this map sheet that was coloured, and it would have retailed for the equivalent of about £140 in modern money. Right, let's go on. So here's Ben Peach's look at that ground and his watercolour from his field notebook. And the other way that knowledge was shared with the world, not just through the published map, but in a paper in 1888, which shows the cross section through that ground. But that's what you're seeing underneath. Right, so beginning to get the knowledge out there. So let's look at the progress of the mapping that developed. So, and it's a long journey. So as we've seen, the mapping started in 1883 in the Durness area. It was Peach and Horne and the new hire I've not mentioned, which was Lionel Hinksman. And then the following year, in 1884, when they moved to Erebol, Peach, Horne and Hinksman were joined by Henry Cadell. And the four of them worked that season. And thereafter, running up to 1887, the gang included Gunn and Clough as well. So there were 6 of them working the ground to Ullapool. It has to be said that the weather through those summers was if you read the reports, was apparently really, really poor. What happened next is they then moved south across Loch Broom and filled the ground in increasingly remote areas all the way to Skye. They had to involve more and more geologists because the range of the geology changed. Woodward, for example, was a world-renowned Jurassic stratigrapher who was brought in for when their map sheets included parts of the Jurassic on Raasay and on Skye. So various people were brought in to expand the team. So a lot of people were seconded into this activity. The final bit of the Moine Thrust belt to be mapped was a little bit in Eastern Assynt, where Pigeonhorn returned in 1896 to complete it. So you've got there a 12 or 13 year history of mapping. It's a really, really long project. But it's not as long as the efforts to publish it. So the initial report of thrusting by Geekie was published in 1884. The work to Ullapool was published in 1888. We've already seen a diagram for that in black and white a couple of slides back by Peach et al. And that only covers the northern part of the thrust belt. The only other significant publication that describes their work really is the classic Northwest Highlands memoir, which was published in 1907. So really, you know, it's 10 years, 11 years after the last bit of mapping was done. And what about the maps themselves? Well, you can reconstruct this history of how the maps were published and linking it to the geological history and why it took so long by digging through the annual reports of the Geological Survey, which were, as it says, published annually. And rather interestingly, they were written by Geekie. Normally it'd be the local director who wrote them up, but Geekie, because he had such a hand in it, wrote up the annual reports for the Moine Thrust belt. Incidentally, I've little plugged this. I've put together the story of that in great detail in a video called Mapping the Zone, and I'll give you the link of that at the end. But here are the sort of the highlights. So, sharing the geology. How have other people discovered the Moine Thrust belt? Bear in mind that in the 1880s, it wasn't that easy to get to. So there are various ways in which the survey team chose to share their knowledge through papers and through museums. I quite like this photograph of the old Geological Museum in Jermyn Street, which shows you that if you have a museum in those days, you wanted to show every possible specimen. So the first really important publication is the 1888 paper by Peach, and some of the diagrams are below, which show the story. They show the idea of low angle, major thrusts, and so-called minor thrust structures they later called imbricates, which create a sort of scaly structure underneath, shown by little t's. So they recognize different orders of thrust, and it's that type of understanding that goes forward to places like the Rocky Mountains in the 1960s, that idea of different scales and continuity of thrusts. The real biggie is the 1907 memoir, which I'm showing the front page of there, and the map that was published with it, which is a remarkable piece. Now, there's been a lot of speculation about why it took the team 11 years to publish the memoir after the last bit of mapping for the Moine Thrust belt was complete. So in other words, they could make that the map on the left was complete. Indeed, it was drafted 3 or 4 years before the memoir appeared. Well, reading between the lines, and actually if you read early historians of the Geological Survey like Bailey, they put the blame squarely on Peach's shoulders, suggesting that he didn't like writing. And if you read between the lines, I suspect Ben Peach was fairly majorly dyslexic, and of course dyslexia wasn't really. It was discovered and more or less put in place as a thing at the start of the 20th century. So Peach was, I think, was an undiagnosed dyslexic. He did all the diagrams. He was happy doing all that. He just, as Bailey put it, could barely read or write. Anyway, on with the story. This map is fantastic. It's a summary map. And this is a bit of the area around that, the Shellock. It's a really great map. And it's the first map from, pretty much the first map from Scotland that was actually printed in colour rather than hand coloured. Right, so how the other ways in which you can, that they try to share the geology and share their discovery of the Moine Thrust. A famous one is the plaster model that was created at a scale of at the scale of 6 inches to the mile. Ben Peach put the map together and drew the side elevations that you can't see on this. This photograph comes from the Grant Institute in Edinburgh. It was actually, the original model was actually made for what is properly known as the Louisiana Purchase Exposition of 1904, generally now known as the Louisiana World Fair, where it was shipped across to St. Louis. I don't know how many people actually bothered having a look at it. I don't know how many people know about the Louisiana Purchase Exposition, but it was essentially a 6-month show that had rodeos and all sorts of stuff. It also had the Olympics held there. So there was all sorts of distractions from the geology, which probably meant it was a hard ask to go and look at a coloured plaster model of part of northwest Scotland. But following that, a whole bunch of copies were made, one of which was put into the Geological Museum in London, another one in Edinburgh, so that people could actually go and experience the 3D geology and the findings of it on the basis of this rather spectacular 3D model. And somewhat later, Peach and Horn put together a guide to this model, which sold for the princely sum of 1 old penny, approximately something like 40 pence in modern money. It's a super bargain by anybody's standards, and it includes diagrams and cross sections and all the rest of it. It was really well regarded at the time, although there was a slightly interesting review in the Geological magazine. I thought I'd share with you this, where clearly somebody in London didn't like the Gallic names of the hills and just wanted them named Hill 60, etc., rather than have to get their head around the names. But otherwise, it was highly regarded. Indeed, that the guide to the model was actually taken back into the field by many people to actually go and visit the sites. So, sharing the knowledge, that they're doing quite well at what we call outreach these days. They did really badly in terms of rigorous publication in trying to share the understanding. Nevertheless, the cross sections that were in Peach et al. 1888 inspired textbooks. So here's a 1912 textbook with cross sections of low angle thrusts and steeper imbricate thrusts, indeed using the term imbricate structure, that was written by Archibald Geekie's brother, James Geekie, which for many editions was the go-to book about structural and field geology. So the insights were very widely shared because they appeared in textbooks. The other way the knowledge was shared, of course, was by taking people onto the ground. So one of the more famous trips was after the British Association meeting. A whole bunch of people went to Assynt. Our friends are here, led by Peach and Horn, slightly older than we saw them when they were sat in the office in Edinburgh. And this photograph is remarkable because it actually shows that they transferred the knowledge to leading exponents of tectonics in Europe, these characters here, who are major alpine geologists. If you want to find out about this trip and its impact, it's worth checking out the paper by Tony Barber that's referenced at the bottom there. So outreach was going apace. But what about the maps? It's a geological survey. They went up there to make maps. And I've been talking about sharing the science and the discovery of the Moine Thrust. Well, the maps, goodness me, they took a time to appear. So this is one of the maps that appears of the Moine Thrust belt on the north coast there. It appeared in 1892. It first tried to come out 3 years earlier, but they had to change the key because the ages of the rocks changed after they realized that what we now know as Cambrian was not Silurian as they thought it was after fossil finds. So they kept having to change the maps. Eventually that one was published. 1892 also saw this sheet. We've already seen this one. It's the Loch Inver sheet. This one here, which is Ullapool, and this one down in here, which you can identify the island of Raasay there, the Applecross area and Kishorn in 1896. You might think, hang on a minute, why have we jumped from Assynt down to Kishorn? Well, that's it. Up until 1896, that was it. 4 maps for the Moine Thrust Belt published. All of these, if we zoom into Knocken, were printed in black and white and then hand-colored by watercolors for sale. And these maps, depending on their complexity, as I said, could retail for anything up to £140 in today's money. So yes, they were publishing maps. They can't produce very many of these hand-colored ones, and they were super expensive. You can't really expect students to buy a set of maps of the Moine Thrust Belt, and they cost 140 quid a pop. So very expensive and limited runs. In 1900, there was a big review of the survey's effectiveness under Geeky called the Wharton Committee Report. And Lapworth was on that. And one of his big issues with the survey progress up there was not the quality of the science, but how they were producing it and how they were sharing it with the public. So let's see what happened. Let's remind ourselves of the extent of the Moine Thrust, and I'll now show you the map coverage. So up until 1908, those are the areas of map that have been published. The majority of them in black and white hand colored, at least for the Moine Thrust Belt bits, the ones on the northwest coast up there. So let's see what happens. 1909, you get that sheet published. 1912 for those two. And what about the final 2 bits, which are sheet 108 and 102? Well, let's go for 102, 1925. And 1931 is the final bit of Moine Thrust Belt to actually appear in a published geological map at a scale of 1 inch to the mile. Why? Well, the first reason, of course, is the transition to color printing. These ones in red were printed directly in color, and the Geological Survey were quite late adopters of color printing, certainly on a European basis. But the other reason was this land, which is Moine. Here's a map, sheet 82. You might recognize the bottom of Loch Carron at the bottom left-hand corner there. And the area we're interested in is the top left-hand corner, which is the Moine Thrust Belt in Shellock. But in order to publish this map, they're not going to publish half of it white. They had to survey the yellow, purple and pink stuff there, which are the Moine rocks, an entirely more complicated bunch of geology. So the presentation and publication of the basic science of the Moine Thrust Belt was delayed because they had to grapple with the more intricate, but perhaps less relevant to understanding the Moine Thrust Belt geology of the Moine. But eventually they did. So here's part of my favorite map sheet of all, which is sheet 92. And indeed, these came out with their own memoirs as well, some of which repeated the contents for the Moine Thrust Belt that appeared in 1907. So eventually they become published, but it took a hell of a time. Therefore, in 1923, probably the most important publication of all came out, which is the Assynt District Special Sheet, 1 inch map shown by the red block. It came out before the last formal map series sheet came out. And you can sort of understand that the survey had so many requests for geological maps of the Assynt area, 2 of which hadn't appeared, and the other 2 were available in some darkened room because they were watercolored, very rare originals by this stage. There were essentially no available geological maps of this area, so they decided to print the special sheet. Here it is in bits. It's a mega classic. For me, it's probably the most inspiring geological map ever produced for understanding tectonics and the quality of work that's represented by the cross sections, which is truly astounding. And it was published straight away in color. Incidentally, if you want to know if you've got an original edition, the thing to do is look for the National Grid. If its National Grid is published with the map, it means that it's not an original. The grids only appear on these maps after the Second World War. Top tip. The other thing, of course, is you can see how popular this map was by looking at its publication history. First appeared in 1923, reprinted in 1947, reprinted with minor changes, 1965, reprinted in 69 and 77 and 86. So it was a hugely popular map, responsible for training of assisting the training of generations after generation of students in map interpretation, basic map interpretation, and more advanced things in thrust tectonics. A hugely influential publication. And of course, people go on to discover the Moine Thrust through TV and film, a couple of things I've been involved with over the years. So you can see the inspirational quality of the landscapes up there. And of course, you can go yourself and either, if you're a student, join one of the field trips, or if you're at a conference and a conference participant, deal with these fantastic structures and be inspired with those, and even get up close and personal with the Arnaboll thrust. So it remains a wonderful place to visit. Go visit the Geopark. They're great places. You don't have to go into the wilds too far. You can go up into Knocken and in 10 minutes get to grips with these fantastic locations, as indeed I did 2 weeks ago. So it's a really wonderful place to go visit. My final slide is a plug, which is that you can follow extra bits of this on my YouTube channel by just Googling the shear zone, and you'll find quite a lot of extra videos, including the one about the history of the mapping on there. But that's me. Thank you for staying awake, if indeed you have.